Alright, now that we've talked about the idea of a one-to-one function, let's talk about the derivative of an inverse function. So I have an example here, a nice simple function, y equals 2x, which we talked about earlier, multiplying and dividing are inverse operations of each other. I've got its graph shown, and then I've got its inverse graph shown as well, which we know is a reflection across y equals x. And we know that its inverse function, which I can denote as follows, is x over 2. And because the blue graph is 1-to-1, it's strictly increasing, which means each x has one y and each y has one x. I know that its inverse will be a function as well. And the question is to find the derivative of the two functions, the original and the inverse, at the points indicated. So for the original function, the derivative would be 2, and in fact the derivative at 3 would be 2, because this is saying the derivative is 2 everywhere, which, because this is linear, means the slope of the tangent line anywhere along the blue line is 2. Now if I do the derivative of the inverse, now the notation here is a little tricky. So the derivative of the inverse, which I can write like that, would be 1/2. And so the derivative at the point I'm asked about, which is 6, is also 1/2. And what I'm going to be driving at here is, do you notice a relationship between the slope of the 2 points I've selected, here and here? Is there a relationship between the two? Looks like perhaps they are reciprocals of each other, which wouldn't be too surprising, because if I think about this top graph, if I go up 2 and over 1, and if the inverse is the switching of the x and the y, then you would think that the 2 and the 1 would flip to 1 over 2, which would give a slope of 1/2. So intuitively it seems that there's a reciprocal relationship between the two derivatives. So let's look at this with another example. Back to our parabola that I talked about earlier. And this time I want to know the derivative at 2, 4 on the original graph, which is here, and the derivative at 4, 2 on its inverse. Okay? Well, again, it looks as though these two slopes may have a reciprocal relationship. So let's check it out. The derivative of the original would be 2x, and the derivative at x equals 2 would be 4. So the slope of the green line is 4. The inverse function is the square root of x, and so the derivative of that is 1 over 2 root x, and I'm asking for the derivative at x equals 4, the inverted point from the original, and if I plug that in, I get 1/4. So again, the inverse point on the inverse has the reciprocal slope to the derivative on the original. So now that we seem to be noticing a connection between the derivative of the original and the inverse, let's try to show this in general. So let's take a one-to-one function, y equals f of x, and its inverse would be x equals f of y. Alright, so here's my inverse, and I want to differentiate. I want to get dy dx. So I'm going to differentiate implicitly. So that would be 1 equals f prime of y dy dx. And so dy dx is 1 over f prime of y. And this is the derivative of the inverse. Another symbol for that would be this. And what we're saying is that it's the reciprocal of the derivative of the original at the inverted point. Alright, now the thing that people get confused about here is which x and which y are we talking about. So this x represents xy on the inverse. This y over here is on the inverse. Okay? If x comma y is on the inverse, we know that y comma x is on the original function. So you can think of this y as the y coordinate of the inverse, or the first coordinate of the original function. Alright, so our conclusion is that indeed the derivative of the inverse function at x comma y is the reciprocal of the derivative of the original function at y comma x. Alright, let's apply the concepts we've talked about to this question. So I have here a function, and you might wonder, is it a one-to-one function? So is it one-to-one? Okay. Well, it's one-to-one, remember, if the function is always increasing or always decreasing. And we can tell that by looking at the derivative of the function. So the derivative of the function is 9x squared plus 2. Now, no matter what x is, positive or negative, this will always be positive. So since f prime is positive everywhere, f is increasing everywhere, so it is one-to-one. In other words, the inverse relation is a function. Okay, so now let's get into the heart of the matter. How do I get the derivative? Well, I could do this one of two ways. I could find the inverse, and I can do that by switching x and y. So here's my inverse. Oops, finish that off. And now I'm going to differentiate implicitly. So 1 equals 9y squared dy dx plus 2 dy dx plus 0. Now I'm just going to factor out my dy dx's as so. And then I'll isolate dy dx. The derivative of my inverse is 1 over 9y squared plus 2. So the derivative of the inverse, another way to write it, is like so. Okay, now what people tend to mix up here is which x and which y are we talking about. On the inverse, the point we're talking about is the point x comma y. Okay? And we are being asked for the derivative at 6. So we know that this point is 6 comma something. The point on the original, therefore, y comma x, was something comma 6. And the y we're looking for, or the y that we need to calculate the derivative at 6, is the y right here. Or the y right here, since they match. Okay? So we're missing something. We need to calculate this missing number. So if I go back to my original function, and I'm going to apply the fact that I know y is 6, and I'm going to need to calculate x. Now you're thinking, oh, this is a cubic equation, this is going to be hard to do. But if you just look at it and try some values, remember there can only be one answer because we've proven it's one-to-one. Each x has one y, each y has one x. You'll see that x is equal to 1 just by good old inspection. Okay, so the x value here is 1, which means the y value on the inverse is 1. So putting it all together, the derivative at the point 6 on the inverse is 1 over, I'm bringing down my derivative from up above here, 9, the y value that goes with the 6 of x, 1 plus 2, and I get 1 over 11. Now there's another way you can handle this, and that's to apply the concept that we talked about earlier. The relationship between the derivative of a function and its inverse at the inverted point. The derivative of the inverse, we said, was simply the reciprocal of the derivative of the original at the inverted point. So do the derivative of this, 9x squared, and switch the x and the y. So it's 9y squared plus 2. Then plug in your specific point. When x is 6, we've calculated that y was 1. Work it out, and 1 over 11.